And this is kind of a fun video, so hopefully it'll work. Again, it's a steal from YouTube. We'll might have to watch an ad. Oh no, look at that. Awesome. Would make it full screen. So, I don't know if you can see these little tiny particles in here and there's stuff flowing, right? That's pollen. So these are actually pollen grains. And it was originally thought that pollen grains and life had this sort of force to it. Oh, sorry, it's a very short video, so I'll go back. Had some vital force to it that caused it to move like that. So Robert Brown saw this, but didn't necessarily understand it. Okay, so let's do another one. Hang on. I guess we'll allow notifications. So let's get rid of this, and let's go to the other one. Let's go to this one. So these are not pollen. This is more like dust. In fact, these ones might be nanoparticles. Yeah, they're nanoparticles. So thinking on the scale again of that multi-walled nanotube, right? This is what they look like. But these are nanoparticles, so not tubes. They're probably short segments of like clusters of material. But they're also moving all the time, right? And look at how crazy they move, right? You could try to track one, but basically they're just moving randomly in all kinds of different directions. Sorry. And so this became known as Brownian motion. Let me close that because I don't want to listen to somebody talking. So this is known as Brownian motion. And in Brownian motion, that's what goes in that slot down there. Particles are in constant motion. Okay, so what does this mean, right? It wasn't until actually early 1900s, and you have to think about this. While atomic theory had been around for roughly 100 years, people didn't necessarily believe it, right? It's a crazy thing to think about. Like we think about atoms. Oh yeah, atoms. They make up everything, right? There's a T-shirt even about that. Don't trust atoms; they make up everything. But yeah, people didn't necessarily believe that, and it turns out like it took Einstein, right, and another guy, and some other people, to do the mathematics to show that you could actually look at Brownian motion. And again, remember the nanoparticles aren't alive, so it wasn't a vital force thing. But they didn't know that way back in the time. They didn't have we didn't have nanoparticles till recently, right? But they were looking at dust particles and stuff too, and they all seemed to have this life force in them, even though they weren't alive. So Einstein was able to show, like you could show that the presence of atoms by studying Brownian motion. And it was later, like in the early, again, still in the early 1900s now, this is just barely over 100 years ago, that a guy named Perrin, and that's spelled, it's not, oh shoot, I think, my best recollection, something like that. Um, uh, oh, actually, no, it's like this. Perrin. Yeah. He got the Nobel Prize for it. He was able to put the experiments together and show that, in fact, Brownian motion was due to having objects that you could see being struck by objects that you couldn't because they weren't like reflecting light or weren't absorbing light. And when they would bounce off of these objects, it would cause that particle to jitter. And it was temperature dependent, and there's a lot of things. There's a way to show that very likely that there are smaller unseen objects running into these. Now you have to think, right, on the scale that we're talking about things that you couldn't normally see, at least back at the time with the light microscope. They're barely under the resolution of a light microscope. So we're talking again, sub-nanometer dimensions. And you couldn't see those things because they don't absorb or refract light probably, and they would hit these other objects with enough kinetic energy to cause them to move. Okay. So that's kind of the bookends, right? We talk about Earth, Wind, and Fire, and then we talk about nanoparticles and their motion. We talk about Einstein and Perrin, and that's kind of the bookends of like atomic theory. But what happened in between, right? Why did we think that they were atoms, right? And so it starts with first the idea of conservation of mass, and a guy named Anton Lavoisier. And you'll notice in pictures of Lavoisier, there's always this woman standing next to him, and that's his wife, who gets credited with helping him, like making all these discoveries. And who knows, maybe she made some of them herself, honestly. But she apparently did a lot of the writing for him and helped him with his work. But he showed that you could have conservation of mass. Now, what does that mean, right? And people will say, well, how could they believe that? I'll tell you a little story at the end, and you'll sort of see the reasoning why it was hard to not believe. But when you burned wood, right, and you weighed the wood and you weighed the ash, remember you can't see all the gases, the oxygen and stuff that was consumed, and the energy that's released, and the carbon dioxide and water vapor that released. You can't see those things, right? So all you can see is the ash. And so you take the wood and you take the ash and you weigh them. But in fact, you don't really have to weigh them. You know that it lost a lot of mass, right? Because all the carbon left and all the oxygen and hydrogen that were in there, most of that all left. You're just left with just some unburnt, unconsumed carbon at the end, and some minerals and other things if it's a plant. Yeah. So they said, well, where did all the mass go, right? And they came up with this idea of phlogiston and caloric. And these were unseen things. The phlogiston is like the mass that was lost, but it was helping bind everything together. And caloric is the energy, right? And so what Lavoisier did is he did very careful experiments, because he realized that if you burn wood, it loses weight. So that could have been phlogiston, but if you burn a metal, it gains weight and it gets heavier. And so he knew that like something was weird. And so what he did is he just did real careful experiments where he took a reaction and carried it out in a sealed vessel, and he weighed it in before and after, right? So you can imagine you take a piece of wood and you stick it in a glass tube and you fill it with oxygen, which you could make, and then you burn it, right? And it burns on the inside, and then you're left with ash, right? And you weigh it before and after. It turns out it always weighs the same amount, right? So basically, conservation of mass. Conservation just means you don't lose anything, right? Conservation of mass says the mass before and the mass after are the same. And that's actually a law, because it doesn't explain why it's the same. Remember we talked about laws and theories? It doesn't explain like, well, we don't lose atoms. It doesn't say anything like that. It just says it's always the same. So that's why it's classified as a law. So the law of conservation of mass, and there's also a law of conservation of energy, just basically say what you had before you end up with the end. Okay. Now it's a funny thing that we think that, oh, why did they believe that? But they actually had a whole mathematical proof of like why phlogiston and caloric exist. And there's a story that goes around about a professor who had a class, and he said he's going to give them a lecture, and he actually gave them the lecture proving that phlogiston exists, and the students completely bought it, like, oh, this has to be it. And then in the next lecture he showed them it didn't exist. So these are all high level science students being duped by an old theory, basically. And so it's not unreasonable to think that the theories that we have now might not be the theories that we have in 10 years, right, for example. And you can't look back at older civilizations and times and think, well, they didn't know anything, right? Because we barely know much more than they do, really. All right. So what really happens when something burns, right? So what really happens when something burns is this. And I'm going to show you a combustion reaction. It's one of the reactions you'll need to know in a later chapter. But let's say you have glucose, C6H12O6. That's its chemical formula, right? When you burn that with water, with oxygen. I don't know where water came from. When you burn that with water, or oxygen, I can't stop myself, you get CO2 and water. And it doesn't matter if it's gas or liquid form for now. And you use 6 oxygen molecules, you get 6 carbon dioxides and 6 waters. And if you add all that up and you add all that up, you'll see that there's carbons, there's 6 carbons, there's 12 hydrogens, there's 18 oxygens. And you'll do the exact thing over here. There's 12 carbons, or 6 carbons. I've been zooming all day, so my head is just a little foggy. 12 hydrogens, and then here you have 12, and then you have 6 more, so you have 18 hydrogens. And that's really what's happened when there's the conservation of mass. Really, you're just not losing any of the molecules or atoms. But somebody had to show that mass was conserved before modern atomic theory could really take off. Otherwise, it's just like you could make up anything. Like, oh yeah, it just went away. I don't know where it went. All right. Here's the reason why metals gain weight, though. If you take magnesium, this is one of the simple ones to show. You can do it with aluminum or anything. But when you burn it, a combustion reaction really is the reaction of anything with oxygen that produces heat. Okay, so this produces magnesium oxide, and this balance is like this. So really what's happening is in a combustion reaction, and this turns out to be a solid, right? In a combustion reaction of a non-metal, like carbon, for example, or hydrocarbons is often what we refer to in these examples. You're burning away something to produce usually something that's 2 gases, right? So you don't see them, you don't weigh them. On the other hand, when you burn a metal, you produce a magnesium oxide, and the magnesium oxide is a solid, so you can weigh it. And basically, you're incorporating oxygen from the air into that final mass, and so that's why they gained weight. Back then, they didn't know. But now, since we kind of believe the idea of atoms, and we've had like a few hundred years to sort of build up on the idea, we kind of guess that that's probably what's going on. All right, it's a good guess. I mean, scientific guess, right? But that's kind of what we think is going on. So, other bits of the theory, history, are there was a guy named Proust, again, early 1800s. A lot of this atomic theory stuff came up in the early 1800s to the 1810s or so. And you don't need to know the dates, and you don't need to know the names. I'm just trying to give you the ideas. Okay, there's one name you have to remember is Dalton. That's the one name. We'll get to Dalton's contributions in a little bit. But Proust was able to show, because he could show conservation of mass, that when you took a compound, right, and you identified its constituent components, you always got the same ratios for substances in that reaction. Okay, so let me say it again, right? Every time you looked at a pure compound, remember we talked about compounds, and you break it up into the elements, that pure compound always has the same ratios of masses of constituent elements. So what does that mean, right? That's that gobbledygook. So what it means is that the mass ratio for, let's say, sodium to sodium chloride, right, or sodium to chlorine for that matter, is always going to be, for example, in this example, this is Na to NaCl, is always going to be 7.7 grams divided by 19.6 grams. It's always going to be, and I will again just use this calculator because I don't like it, but it's just there. Sorry. 7.7 divided by 19.6. And it's always this number, 0. Oh gosh. All right, let's do it again. 0.39, and then I forgot the number in my confusion. 39286. Oh gosh, look at that. 3939286. And that's a mass ratio. So the mass cancels out, but it's sodium to sodium chloride. So that's always the ratio for that element to the compound, or you could also do the element to element, so you could get a mass ratio for sodium to chlorine, for example, and that mass ratio of the constituent elements is always the same. Constituent meaning, right, the things that make it up is all. Now, it turns out, besides that, this also has a very practical use, and you could use it to solve problems like how many grams of sodium chloride are produced from 15.8 grams of sodium. The way you could do that is you could say, well, I'm looking for grams of sodium chloride, right? It's a dimensional analysis problem. And I'm going to start with the 15.8 grams of NaCl, right? And then I'm going to go like this. It's 19 points. Oh, sorry, this is grams of sodium. Sorry. It's 7.7 grams of Na for every 19.6 grams of NaCl. So knowing these ratios is actually practical in the sense like you don't actually need to know chemistry to do this. You just need to know the mass ratios, which is actually chemistry, but it's a little friendlier. You can calculate the mass of sodium chloride that you would produce starting with that many grams of sodium. So again, pulling out my handy dandy but not loved calculator, I'm going to say 15.8 times 19.6 divided by 7.7. I'm just doing the math. I should get about 40.21 grams of NaCl. Now, I have only 2 sig figs here, so I should only have 2 sig figs here. So this is a weird one, but you would write it as 40 point and then grams, because that'll give me 2 sig figs of NaCl. All right. So let's show that these two samples demonstrate or don't demonstrate definite or sometimes constant is the word, right? That's another word used. Definite proportions. You notice I put here constant here. They're also known as constant proportions. And how would you do that, right? Again, this is for the amount of sodium and for the amount of chlorine. So what you're going to want to do is you're going to want to set the mass ratio up for that and then do the calculation based off that mass ratio. Okay, so how do you go about setting up the mass ratio? Okay, in order to set the mass ratio up, what you're going to want to do is take the mass of one element in a compound after you decompose it and just divide it by the other elements or one of the other elements. Okay, so for example, in this case it's sodium and chloride. So I'm going to take the chlorine and divide by the sodium. There is no real rationale for what you choose other than it should be something that's easy to interpret and that you can do for all of the substances. Okay, so I typically like to choose the masses, so the larger masses on top. That's all. So I'm going to go 60.7 grams of chlorine for every 39.3 grams of sodium, like that. And then I'll do that for the other compound as well. So I'm going to take, for example, or the other sample, I'll take 35.44, and I'm going to divide that by 22.99, and that's grams of chlorine over grams of sodium. So what's going to happen here, actually, just an interesting thing with the units. The grams will cancel, but the labels stay because you can't cancel them because they're not the same. But the unit mass is the same. It's just the labels that persist. And so this is going to tell us the chlorine to sodium ratio. So I'm going to pull up my calculator. And I'm going to do 60.7 divided by 39.3. And I get 1.54, right? 1.5445, and that's chlorines to sodium. Okay, now that's a mass ratio, but still that's the number you get. And I'll do the other one. And that's going to be 35.44 divided by 22.99, and make sure I got the right thing there. There we go. 1.54, roughly 2. Okay, so when you look at these two numbers, they're not quite the same, but we have 3 significant figures, right? So to 3 significant figures, these numbers are the same. So this is demonstrating definite proportions. If it hadn't demonstrated definite proportions, then the numbers wouldn't have been the same, okay? So this is kind of one of the things that um, Proust showed early on is that when you take a substance, and it doesn't matter where the substance comes from or how it's produced, those mass ratios are always the same, and that's how you know it's the same compound. Now, it turns out that there's another uh, early law of materials, and that was known as multiple proportions. Okay, law of multiple proportions. I don't know why that's formatted so it's all the way to the right, but it is. Um, and when you take two substances and you decompose them, if the mass ratios, okay, so let me back up for a second. You have to have two substances made of the same elements. And if you took the mass ratios, right, and you calculated them and they weren't the same, then it turns out what happens is those ratios are always some whole number proportion of each other. Okay, so I'll show you what that means, but think about that. If the numbers aren't the same, you can actually take a ratio of those, and that ratio will resemble a ratio of whole numbers. And I'll talk about like what that means when I do the calculation. Okay, so I'm going to say I'm going to do, let's say, oxygen over hydrogen. Oh, I didn't explain to you like why I do it that way. It's just because I like whole numbers, and I like seeing numbers bigger than 1. It's easier for my brain to connect to things. When I'm looking at like 0.0356, I'm always looking at that number thinking, what does that mean? But if I saw something like, 14.5, that kind of has more meaning to me. So I always try to make my ratios that when I do them, they're always bigger than 1, just because intuitively I have a better feel for what whole numbers mean. Okay, so I'm going to do this one. I'm going to do 35.1 grams of oxygen divided by 4.39 grams of hydrogen. Now, when you do that calculation, you're going to get 8.00. Okay, and that'll be oxygens to hydrogens in that substance. So we're going to do sample 2 and do the calculation. And you're going to go 4.45, right, grams of oxygen for every 0.278 grams of hydrogen. And then when you do that math, what you end up getting is 16.0 oxygens to hydrogen ratio. So let's think about what this means, right? If you think about these two, this is not showing definite proportions. If it was definite proportions, then those numbers, they would have been the same, right? But what it's showing is multiple proportions, because 16, right? Oops, sorry, didn't mean to zoom like that. 16.0 divided by 8.00 gives me 2 as the number, or a whole number ratio of 2 to 1. Now, sometimes ratios don't come out nice like that. Sometimes it's 3 to 2, which would be 1.5, or 2 to 3, which would be 0.666 or whatever. But again, when you do this division, always choose it so that you get a number bigger than 1, because I think people interpret 1.5 as 3 over 2 better than they interpret 0.667 as 2 over 3. Just a way people's brains work, I think. Okay, so what does this mean? What it actually means is in compound 1, I had a ratio of oxygen to hydrogen that was 8, right? In compound 2, what I have is a ratio of 16. So it means that there's twice as much oxygen in that compound for the amount of hydrogen that I have. Right? And it's exactly a whole number ratio. So whenever they did an experiment like this, right, they always got increments that look like, oh, there's a whole number of these more than it was in the other compound. So how does it happen that it's always a whole number? And this was kind of a big leap. And this is done by John Dalton, and in essence, it led him to the idea that atoms must be unique entities, right, that have their own properties. And so that when you doubled the oxygen, you're actually adding another oxygen, and the word is atom, right? You're adding another oxygen atom by increasing that proportion by a whole number. So, what the law of multiple proportions said, and it's from 1804, and I was actually lucky enough to go to England and go to the Royal Society and got to see a lot of John Dalton stuff. And this is actually a picture of a book that he signed for somebody, and it has something that I can't read, but that's his signature at the bottom and stuff. What John Dalton said is when two elements, and we just call them A and B, form two different compounds, the mass of B that combines with 1 gram of A can be expressed as a ratio of small whole numbers. So now when we got the number 2, what that meant was it's a 2-to-1 ratio, right? Now, from that, Dalton developed atomic theory. Okay, and so this is John Dalton's atomic theory, and actually this is kind of John Dalton's models, right? He actually made models to try to figure out, like, well, how do these things go together if they're whole number ratios? He was trying to work with the geometry, and he did a lot of stuff that when you look back at it now, you're like, you weren't too far off, actually. And you also have to consider, like at this time, early 1800s, right? That was sort of the transition from a lot of alchemy towards more chemistry. So he had alchemical symbols for different substances in his notes, like for acetic acid and for other things that they thought were like unique and pure substances, and actually that they were composed of other elements. Okay, so they thought like different things that we know as compounds, two or more elements, were actually their own element on their own, and then atomic theory helped to decompose that idea, to use the phrase, into the idea that there were atoms. Okay, so here's his John Dalton's atomic theory, and I would like you to know what these things are. Okay, it's not that important, but I would like you to know some of the elements, quote unquote, a pun, of his theory. So each element is composed of tiny indestructible particles called atoms. So matter wasn't just this homogeneous mixture of substance. It was actually unique individual atoms, right? And all atoms of an element have the exact same mass and other properties that distinguish them from atoms of another element, okay? Now, when you have compounds, then he said, right, and atoms combine in simple whole number ratios. This comes from his multiple proportions idea, that form molecules of compounds. So we have a compound. Now we have the idea that molecules are what make up the compound, right? And then he said in a chemical reaction, this is actually a very clever thing, right? In a chemical reaction, atoms of one element cannot change into atoms of another element. They simply rearrange the way they're connected. And so John Dalton literally had wooden, I don't know how he made them so round, because you think about it, that was probably much harder to do in those days. He made these round spheres, and he would play with them in combination to see how the atoms were combining to make one substance into another substance. Okay.